We are very fortunate today to have Dr. David Goodstein, who is Vice Provost and Professor of Physics and Applied Physics at the California Institute of Technology. He has been there for more than 35 years. In 1995, he was named the Frank J. Gillon Distinguished Teaching and Service Professor. In 1999, Dr. Goodstein was awarded the Ørsted Medal of the American Association of Physics Teachers, and in 2000, the John P. McGovern Medal of the Sigma Xi Society. His book, States of Matter, published in 1975, was hailed by Physics Today as the book that launched a new discipline, condensed matter physics. His research in experimental condensed matter physics has dealt with phases and phase transitions of adsorbed two-dimensional matter, ballistic phonons in solids, superfluidity in liquid helium, and critical point phenomena. He is currently working on a future flight experiment that will examine the dynamics of the superfluid phase transition in the absence of gravity. Dr. Goodstein has served on numerous scientific and academic panels, including the Standing Review Board of the Keck Telescope and the Committee on Equal Opportunities in Science and Engineering, an NSF oversight committee that reports directly to Congress. He currently serves on a number of National Science Foundation advisory committees and is a founding member of the Board of Directors of the California Council on Science and Technology. Born in Brooklyn, New York, Dr. Goodstein attended Brooklyn College and received his PhD in physics from the University of Washington. He lives in Pasadena with his wife, Dr. Judith Goodstein, who is here today, who is a faculty associate in history at Caltech, where she serves as university archivist. They have recently co-authored a best-selling book entitled Feynman's Lost Lecture. And of course, he's widely acclaimed and one of the New York Times bestseller list authors for his Out of Gas, The End of the Age of Oil. And it is on this topic that he'll address us today. I'm delighted to welcome you, Dr. Goodstein.
Thank you very much. Can we have a... I'm sure this will work. Oh, yes, it does. Okay. So the cover up here is a cover of a book that I wrote a couple of years ago, and by an astounding coincidence, it has exactly the same title as today's talk. Out of Gas, The End of the Age of Oil. Let's start with some myths about oil. $3 a gallon is too much to pay for gasoline. At $3 a gallon, that's 75 cents a liter. We pay twice that much for bottled drinking water. The fact is that gasoline is just about the cheapest liquid you can buy in the United States, and it would be at $3 a gallon as well. And that's a big part of the problem. Oil companies produce oil. At least they say they produce oil. They talk about production, rate of production, and so on. In fact, no oil company has ever produced a drop of oil. Oil was produced by the sun and the earth over hundreds of millions of years. The oil companies merely extract it and sell it. That's why it's so cheap. We must conserve energy. The conservation of energy is one of the deepest laws of physics. Energy is always conserved no matter what we do, and we don't need to conserve energy. There is something we need to conserve. It's called fuel, but not energy. When we run out of oil, the marketplace will take over and replace it with something else. We will look very carefully at that argument in the course of today's discussion. There's enough fossil fuel in the ground to last for hundreds of years. We will look very carefully at that as well. Nuclear energy is dangerous. At least most people think it's dangerous. Most technically trained people understand that it is the cleanest, most dependable source of energy we have, but it will not solve all of our problems. The greenhouse effects of global warming are bad. I will argue that without the greenhouse effects from global warming, we would not be here. So let's go on with the talk. A brief history of energy. In the 18th century, energy, there was heat was thought to be a fluid called caloric. It was a precise mathematical theory. If you had a hot piece of copper of a certain size, it contained a certain amount of caloric. If you put it into a cool glass of water, you could calculate with precision the amount of caloric that would run out of the copper into the water and predict the temperature at which the two bodies would come to equilibrium. However, not everybody agreed, and Count Rumford, who was born Benjamin Thompson and became Sir Benjamin Thompson later, was one of those who disagreed. He fought on the wrong side in the Revolutionary War, went into exile in England and later in Bavaria, where the Count of Bavaria named him Count Rumford. He's most famous for an experiment he did in which for an observation he made, actually, in which he observed that the boring out of cannon barrels seemed to create a lot of caloric where none existed before, and that should not have been possible according to the caloric theory. He even made an attempt to find out how much mechanical action it took to produce a certain amount of heat, but it was unsuccessful. The law of conservation of energy was discovered at least 9 separate times between Rumford and James Prescott Joule, but the credit for making the discovery goes to the person who discovered it not first but last, because he discovered it so well that it never had to be discovered again. His name was James Prescott Joule, and in his most famous experiment, he had a horizontal paddle wheel in water activated by means of weights that descended a distance of 12 feet, one after another, until 16 weights had descended. And then he measured the temperature of the water with a sensitive thermometer. And he did 3 other experiments of similar kinds and averaged all the results. And he announced to the Royal Society of London that the amount of heat required to raise 1 pound of water by 1 degree Fahrenheit was equivalent to the amount of work required to lift 800 pounds through 1 foot. And that constituted the discovery of the law of conservation of energy. Energy comes in various forms. There is kinetic energy, which is the energy of motion. It can be organized kinetic energy as a car rolling down the street or a bowling ball rolling down the alley. Or it can be the random kinetic energy of the atoms and molecules that make up the car or the bowling ball. The absolute temperature of any body is directly proportional to the kinetic energy of the random motions of its atoms and molecules. So when a thing gets hotter, it just means that its atoms and molecules are moving around faster. Then there's potential energy, gravitational potential energy of the kind that Joule endowed his weights with. There's chemical potential energy. We will be discussing hydrocarbons today, so let me talk about hydrocarbons. Hydrocarbons have a great deal of chemical potential energy. They consist of long molecules of hydrogen and carbon. They can go into more stable molecules, carbon dioxide and water, and give off the excess energy in the form of heat. So that's their potential energy. There's chemical potential energy, nuclear potential energy, and so on. There's one more form of energy that's important to our story, and that's thermal energy, thermal radiation energy, the form in which energy reaches us from the sun across 93 million miles, or almost nothing at all. This is a plot of intensity on the vertical scale versus frequency on the horizontal scale. The frequency scale goes from radio waves to infrared to a narrow band of frequencies that we can see that go from red to blue, and then beyond that to the ultraviolet to X-rays and gamma rays and so on. The lowest curve on this plot might be the temperature of your own body. It rises into the infrared. Everybody radiates all the time. This coolest body, the radiation rises into the infrared and falls back to 0 before it reaches the visible. You don't glow in the dark because you're just too cool. The second highest curve is somewhat higher. It has a maximum in the infrared, but it goes down through the visible. Highest at the red end, and so it looks red to your eye. That might be the temperature of an ember in the fireplace. The upper curve is the temperature of the sun. The sun's maximum is very close to the visible. By no accident at all, our eyes evolved to be most sensitive to the color of the sun as it reflects from the objects around us. With that information, we can talk about the thermal behavior of the Sun-Earth system. The Sun is very hot. Internally, its surface is about 5,800 degrees Celsius. And at that hot temperature, it radiates white light uniformly in all directions. Some 93 million miles away, the tiny sphere of the Earth intercepts a minute fraction of that energy, and 70% of the energy that falls on the Earth is absorbed by the Earth, 30% is reflected. The reflected portion can be seen from the Moon in this picture of Earthrise seen from the Moon, and seen in the colors of the oceans and the continents and the ice caps and the clouds. The 70% that's absorbed must be re-radiated because otherwise the Earth would be warming up, and it's not warming up. It's a simple calculation to figure out what temperature the Earth would need to have in order to radiate the amount of energy that it receives, and the answer is 255 kelvins, or minus 18 degrees Celsius, or 0 degrees Fahrenheit. I believe that if this were the whole story, if the Earth's temperature was 0 degrees Fahrenheit, the mean surface temperature of the Earth was 0 degrees Fahrenheit, we would not be alive. There are various factors that govern the climate of the Earth. One of them is the tilted axis. When the Earth is at position A, the axis is tilted so that the north faces the sun, and it's summer in the north. When the Earth moves around to position C, it's still tilted in the same direction because it's a gyroscope, but now the south is facing the sun, and it's summer in the south. So the tilted axis governs the seasons. The El Nino cycle occurs because of the more or less stable configuration of winds on the Earth due to the Earth's rotation and the action of the sun. The waters of the central Atlantic go across the Atlantic from South America towards Asia. The sun-warmed surface water pile up against the Asian continent and create the monsoons, which are the characteristic climate of that part of the world. But once every few years, once every 3 or 4 years, for reasons that nobody knows, the trade winds slacken, the water spreads back out across the Pacific Ocean, and the result is droughts in Australia and Asia, and storms in North and South America, and a huge perturbation of the world's climate system. The thermohaline flow is particularly interesting. The waters of the Atlantic, the surface water of the Atlantic flows north, getting saltier as it goes because of evaporation, and also getting colder as it goes because of mixing with cold water. Both effects make it denser, and at a point a few hundred kilometers south of Greenland, it becomes too dense to float and it sinks. The water that sinks there will not emerge at the surface again for 1,000 years. It flows in the opposite direction, deep below the surface. It flows down around the tip of South America into the Indian Ocean and into the Pacific Ocean, where it eventually emerges again and comes back. The Gulf streams that warm western United States and Europe are offshoots of this giant thermohaline flow, so this has a great deal of effect on the climate. But by far the most important effect is the greenhouse effect. The greenhouse effect works like this. The light from the sun, the Earth's atmosphere is pretty transparent to light from the sun, so the light comes through it. And then the Earth tries to re-radiate it at 255 kelvins. But the atmosphere contains trace gases that are not transparent to the infrared radiation that the Earth is sending back out into space. The greenhouse gases, so-called greenhouse gases, include water vapor, methane, carbon dioxide, and so on. And before the industrial age, before we started pumping carbon dioxide into the atmosphere, we had an 88% greenhouse effect. That is, 88% of the light, of the radiation from the Earth was intercepted in the atmosphere and re-radiated both out into space, where it balanced the books, radiating exactly the right amount out into space, and back down to the Earth, where it warmed the Earth from 255 kelvins to 287 kelvins, or 14 degrees Celsius, or 57 degrees Fahrenheit. And at that comfortable temperature, we evolved, climbed down from the trees, and started building steam engines. There are important feedback effects when you do something like this. For example, the warming of the atmosphere due to the greenhouse effect melts the polar ice caps. The melted polar ice caps reflect less light from the sun, so that it tends to enhance the effect. It tends to multiply the effect because it's in the same direction as the greenhouse effect, and it makes the Earth warmer. On the other hand, the melting of the polar ice caps freshens the northern water. That is, it makes it less salty, and it could turn around the giant thermohaline flow that we discussed before and lead to global cooling rather than global warming. So with all these contradictory effects on the Earth, that's too complicated for a mere physicist like me to concern himself with. So we like to look at limiting cases. And there are two limiting cases we can look at. One of them is the case in which the greenhouse gases are removed completely. The temperature of the Earth would immediately fall to 255 kelvins, or 0 degrees Fahrenheit. But at that temperature, the oceans would freeze, the Earth would become much shinier, and the temperature would fall much further still. On the other hand, you might ask what would happen if we increased the 88% pre-industrial greenhouse effect to 100%. We don't know exactly what would happen, but we have a very good model to look at. The planet Venus is somewhat closer to the Sun, so it should be somewhat warmer than the Earth, but that's a very weak effect. So Venus could be very Earth-like in temperature, but we know that it isn't. The Russians dropped a probe to the surface, and we know that the surface of Venus is hotter than molten lead, because Venus has a runaway greenhouse effect. And so the Earth could be a frozen wasteland, or it could be a Venusian inferno. Instead, it's this Garden of Eden that we have, that we must protect. This shows the temperature of the Earth in the middle, the red trace, against the concentration of greenhouse gases. The upper trace, the blue trace, is the carbon dioxide in parts per million. The lower trace is methane in parts per billion. And you can see that the temperature pretty well tracked the greenhouse gases over the past 400,000 years. The past 10,000 years, the temperature stabilized at near the high end, and that's the period during which civilization emerged. In the past 200 years, it's not shown in this graph because this graph deals with much longer time periods, but in the past 200 years, the amount of carbon dioxide has increased by 30%, from 280 parts per million to 380 parts per million, and the amount of methane has doubled. And if the temperature follows that trend, as it's followed all previous trends, the results will be catastrophic indeed. We are doing an uncontrolled experiment with the climate of the only planet we have. It's a very foolish thing to be doing, but we are doing it. So, where does useful energy come from? Before 1800, energy came from the light from the sun. The light from the sun warmed the atmosphere and grew our plants and fed and warmed our animals and so on. Some coal was used, particularly in the last 200 years when trees started to become scarce in Europe, and coal was used for space heating. Oil was known through natural seepages at the ground, and there was something called swamp gas, which was analyzed in around 1800 by Alessandro Volta to be methane, Methane is the principal ingredient in natural gas. So the three basic fossil fuels, coal, oil, and natural gas, were known about, but very little used until 1800. In 1765, a young mechanic named James Watt was fiddling around with a steam engine trying to fix it when he thought of a better way of making steam engines. James Watt's better way of making steam engines kicked off the Industrial Revolution. By the turn of the century, two things had happened. One of them is that people were building railroads, and railroads needed coal for fuel. But the other thing that happened was that railroads provided stable roadbeds so that coal could be transported over long distances to urban centers. And both of those effects increased the need for fuel. There was a need for better illumination because of the rise of urban centers. Illumination had not changed since antiquity. For a while, whale oil was popular for this purpose, and whales were hunted. But by the middle of the century, the 19th century, the whales were becoming scarce, and something else was needed. And Edwin Drake, a retired railroad conductor, drilled the world's first oil well in northwest Pennsylvania, near Titusville, and struck oil. At first, the oil was used for illumination and lubrication, but in 1861, Nicholas Otto, a German entrepreneur, invented the world's first gasoline-burning engine, and soon the oil was in great demand for fuel, and oil wells were being drilled all over the world. The net result of all of that is we can no longer live on light as it comes from the sun. We are thoroughly dependent on oil, and the supply of oil is finite. It will eventually run out. So we have unwittingly created a trap for ourselves because we have built a civilization on the use of oil, and the use of oil will come to an end. This graph from British Petroleum, the left-hand side shows where the known reserves are. 2/3 are in the Middle East, no surprise there. 10 times as much in the Middle East as in South and Central America, 10 times as much as in Africa, 10 times as much as in the former Soviet Union, 10 times as much as in North America. The fact is that the Middle East is the only game in town. It's the only thing that counts. All the other contributions are trivial. The right-hand bar chart shows how much there is in reserve in 1981, 1991, and 2001. The units are in thousands of millions, that is billions of barrels, and there are just over 1,000 billion barrels or 1 trillion barrels in the ground where we know where to get it, and that's about a 40-year supply. So that's very comforting, but as we'll see, that's the wrong way to look at it. Marion King Hubbert was an oil geologist who grew up in Texas but wound up at the University of Chicago somehow and got all his degrees there. Had a very unhappy time teaching geophysics at Columbia University and made his career at Shell Oil. And he was at Shell Oil in 1956 when he made his prediction that the oil dominance of the United States would come to an end around 1970 when oil production peaked in 1970. He had data of the kind shown on the lower graph up to about 1950 at the time, and he knew that the oil discovery in the United States had peaked around 1930. The oil production follows oil discovery by a few decades, and he used that information to predict that the oil production would peak around 1970. I beg your indulgence to use a few equations here, very few equations, but this is supposed to be a technical audience, so I thought I could do that. Let Q be all the oil that's been discovered, and Q naught be all the oil that ever existed. At first, the discovery grows exponentially, so it follows the differential equation for positive exponential growth, dq dt equals aq. But after a while, the exponential growth slows down because you've started to use a finite amount of the oil and the oil is harder to find. That can be modeled by multiplying the right-hand side of the equation by Q0 minus Q. The result is called the Logistic Equation. It's an equation that's widely used in business schools and by ecologists. It's not much used in physics, but it could be. This is a graph of QDT versus Q. It's actually the catches of a certain kind of fish versus the available biomass, and you see the nice parabolic curve. Depending on what assumptions you make, you get different curves. I got this off the web. But what we would like is not the QDT versus Q, but the QDT versus time versus T, to have this kind of behavior. And to do that, you must solve the differential equation. The solution to the differential equation is the QDT equals Q0 times A e to the A T0 minus T over 1 plus E T0 minus T. T0 is the time of the peak, and T runs from minus infinity to plus infinity. This form looks unfamiliar to a physicist because physicists don't use this equation very much, but if you plot it, it looks very familiar to a physicist. It is a typical bell-shaped curve. I think the reason that Hubbert used this equation rather than a Lorentzian or a Gaussian, there are the other bell-shaped curves, is because if you plot 1 over Q the QDT, that is the percentage of discovery per year, against Q, you get a straight line that intercepts the axis at Q0. And that tells you how much oil was ever produced by nature, and Hubbert did that. This is the actual data, and the kind of curve that Hubbert used is shown in red, and the actual data is shown in black points. And as you can see, he was spot on. He was right on. The United States oil started to run out in around 1970. So these data are the same for the world as Hubbert had for the United States, and should make it possible for us to predict the worldwide Hubbert peak. The left-hand graph shows the proved reserves, and you can see there was a step function in the late 1980s, a big increase in OPEC countries' oil reserves. That came about not because of any discoveries. If you look on the right-hand curve, you can see that there were no discoveries, no important discoveries in the late 1980s. Instead, OPEC changed its quota rules for how much oil each country could pump, based in part on how much it had in reserve, and the reserves appeared by magic out of nowhere at all. These are not geological oil reserves, these are political oil reserves. The right-hand graph shows oil discovery and oil production or usage, and you can see that the discovery peaked around 1960 and has been declining ever since, and that the production of oil, the usage of oil, crossed the discovery curve around 1980. So for the past 25 years, we've been using oil faster than we've been discovering it. Of course, the reserve should have been going down for the past 25 years. Instead, they go up always because they are political, not geological numbers. In any case, the kind of information in the right-hand curve is just the kind of information that Hubbert had when he made his prediction for the United States. So we should be able to make a prediction for the whole world based on these data. Here is one such prediction. It was published in Scientific American in 1998. The upper curve is the same curve we saw on the last slide, the production. The lower curves are just partials that add up to the upper curve. And the prediction calls for a peak right about now. Now, there's no telling what will happen when this peak arrives, but we've had a couple of dry runs. Back in 1972 and again in 1979, we had little peaks because the Arabs countries embargoed the oil to take advantage of the lack of oil in America. And then the second peak occurred because of the Iranian Revolution. The immediate result was mile-long lines at gas stations and despair for the future of our way of life. When this peak occurs, it will not be temporary. it will be permanent and forever, and so we will be in deep trouble. On the other hand, you have to use a certain amount of caution in evaluating a prediction like that because there are a number of factors that are variable. For example, they used 1.8 trillion barrels for the total amount of oil that nature ever made for us. Using Hubbert's technique, it looks like, extrapolating to Q0, which is the total amount of oil that nature ever made for us, it looks more like 2 trillion barrels than 1.8 trillion barrels, and that would put off the peak for a few years. New technology is the equivalent of new discovery. That is to say, it makes more oil available, and so that will help. The increasing price of oil, when the price goes up, as it has recently, it makes more oil available because you can apply more technology to get more oil out. And finally, the reserve numbers, the numbers of mountain reserve, as we've seen already, are very soft. And so we can't tell how much reserve there really is. And so for all those reasons, these predictions might not be accurate, but the basic idea is right. The basic idea is that oil, like any natural resource, starts at zero, rises to a maximum that will never be exceeded, and falls back to zero again. And we will be in trouble not when we pump the last drop of oil out of the ground, but when we reach the maximum, which is roughly the halfway point. And we have reached roughly the halfway point now. We have used 800 billion barrels of oil. There are 2 trillion barrels of oil in all, and so we're very close to the halfway point. Ken DeFaze, who is an oil man, said he knew that Hubbert had been right and that the United States had peaked when he saw this announcement in the San Francisco Chronicle in the spring of 1971. The Texas Railroad Commission announced 100% allowable for next month. To those of us who are not oil men, that requires a little bit of interpretation. The Texas Railroad Commission was the quaintly named cartel that governed the supply of oil in the United States by manipulating the excess capacity of Texas. When it announced 100% allowable, it was announcing that it had lost control of the market, that Texas could pump flat out, and it no longer operated as a cartel. Soon after this announcement was made, OPEC was formed, the Organization of Petroleum Exporting Countries, to do for the world exactly what the Texas Railroad Commission had done for the United States, to govern the supply of oil by manipulating the excess capacity of Saudi Arabia. So I've always thought that the fact that the peak had been reached worldwide would become clear from the announcement that Saudi Arabia had peaked, was running out of oil. Exactly that announcement was made on February 24, 2004, in a front-page story in the New York Times. Forecast of rising oil demand challenges tired Saudi fields by Jeff Girth. It goes on to say the country's oil fields are now in decline, prompting industry and government officials to raise serious questions about whether the kingdom will be able to satisfy the world's thirst for oil in coming years. Now, this was a New York Times story, so it was very long, and it was written in a style in which each paragraph contradicts the previous paragraph. That's called balanced reporting. And so somewhat further on in the article, it says some economists are optimistic that if oil prices rise high enough, advanced recovery techniques will be applied, averting supply problems. But it takes it back in the next paragraph. But privately, some Saudi officials are less sanguine, and so on. I don't know whether we will eventually look back and find that February 24, 2004 was the date that the worldwide Hubbert's peak was reached. We're much too close to the situation to tell. It could still be 10 years off or 20 years off, although the volatility of oil prices recently implies that it's very close. However, to those who are aware of the Hubbert's peak predictions, as this author of this story was apparently not, this was a chilling story indeed. So who needs oil? Well, oil is used for petrochemicals. There are 6.4 billion people living on Earth today, most of them reasonably well fed, as a consequence of something called the Green Revolution that took place in the second half of the 20th century. The Green Revolution consists in large measure of fertilizing fields using petrochemical fertilizers. I don't think that we could support the 6.4 billion people that are alive today, much less the number that are expected by the year 2050, without petroleum. Petroleum is used in stationary power plants, although in that application it can be substituted easily by nuclear or natural gas. It's used for home heating, so if the price of oil goes way up, a lot of homeowners are going to be disadvantaged. But its most important use is in transportation, where cars, trucks, planes, ships, and trains all run on oil, and it's hard to see how they can run on anything else. This gives an idea of the global consumption of energy. The units are terawatts. Oil, gas, and coal, 3 fossil fuels, add up to a total of 10 terawatts. Half of that is oil. There are a number of other sources: hydroelectric, biomass, renewable sources, and nuclear. And the total is 13 terawatts. This was for 1998, but the numbers haven't changed all that much since then. The total is 13 terawatts, of which the United States uses 1/4. We, with 5% of the world's population, use 1/4 of the world's energy. We are profligate users of energy. 99 quads. Quads are quadrillion British thermal units, a unit you will not hear again in this talk. The economists assure us that when the oil starts to run out, it will be replaced by something else. Well, let's look and see what something else consists of. Oil refers not only to the light crude oil that we've been using up to now, but also to heavy oil and oil sands and tar sands. Heavy oil is basically what's left behind in oil fields when the light crude has been pumped out. You can always pump a little bit more out from any oil field by using advanced technology. The more you pump out, the heavier it gets. The oil sands of Alberta the tar sands of Alberta have been renamed oil sands because that attracts investment. And they are now being exploited successfully at $50 or $60 a barrel. The oil sands of Alberta are being exploited, but what comes out of the oil sands is not oil. It takes 2 tons of ore, strip mined ore, to make 1 barrel of substance called bitumen, which is not rich enough to distill into oil. So hydrogen must be added. So some of the world's largest plants for extracting hydrogen from natural gas have been built in Alberta, and that's characteristic of all of these other sources of fuel. They become more and more expensive, both in resources and in money, and eventually they're not worth the trouble. Natural gas is a very good substitute for oil, but because it can be liquefied and turned into a liquid fuel or compressed, and use this compressed natural gas in our cars. But the Hubbert's peak for natural gas is expected to be only 10 or 20 years behind the Hubbert's peak for oil, so it's a temporary solution at best. Shale oil is unborn oil. That is to say, oil is created when organic matter sinks beneath the surface of the oceans, deep into the earth. The interior of the earth is heated by natural radioactivity, and if it sinks to just the right level, it gets cooked into oil. If it sinks too far, it gets overcooked and becomes natural gas. If it doesn't sink far enough, it becomes shale oil, but shale oil is unborn oil. Shale oil can be turned into oil by heating it in a retort, a process that's environmentally extremely damaging. Those who have invested hundreds of millions of dollars in shale oil have sold off their investments because they've decided that shale oil will never be energy positive. Whether it will or not remains to be seen, but it's not the solution to our problems. Methane hydrate is a solid that looks like ice but that burns when it's ignited. It consists of methane in a cage of water molecules. It's created when methane comes into contact with water under low temperatures and high pressures. Nobody knows where it might be found, how much of it there is, and how it might be exploited, but stuff does exist. And then finally there's coal. We're told that there's enough coal in the ground to last for hundreds or thousands of years at the present rate of extraction. The fact that the estimates of how much there is range over a factor of 10 from hundreds to thousands of years tells you that nobody knows how much coal there is, has any idea of how much coal there is. But that's fairly dependable compared to the second part of the phrase, at the present rate of consumption. The largest deposits are in the United States, but there are large deposits in Russia and China as well. It can be liquefied and used as a substitute for oil. That was done during the Second World War in Germany, because the Germans had coal but no oil. But it's a very dirty fuel. It contains impurities like mercury, arsenic, and sulfur that are very difficult to get rid of. It's the very worst fuel from the point of view of the greenhouse effect, because it's all carbon, no hydrogen. You would have to increase the rate at which it's extracted by at least a factor of 5 if it's to replace the oil, which constitutes half our use of fossil fuels. And the extraction and conversion process is inefficient, so you'd have to mine it 5 times as fast on an almost unimaginable scale. But even that ignores the increasing population of the Earth, the fact that the poorer parts of the Earth would like to have a higher standard of living and therefore burn more fuel like we do. And finally, the Hubbert's peak effect, which is just as valid for coal as it is for oil. And so I think, all things considered, if we turn to coal to substitute for oil, we will start running out of coal by the end of this century. So what does the future hold? Well, there will be an oil crisis very soon. Whether the oil crisis is already upon us, which is quite possible, or it won't be upon us for another 10 years or 20 years, I don't know. But we can predict that there will be an oil crisis very soon. In any case, the fossil fuels, if we substitute coal for oil and go on muddling along, the fossil fuels will start to run out by the end of this century. Doing that has unknown consequences for the climate of our planet, and so it's a very foolish thing to do. But even if we survive that, we are left with the problem of creating a civilization as complex as the one we have now, running entirely on the solar flux, the solar energy that comes to the Earth, plus nuclear, because those are the only 2 sources of fuel we have, the only 2 sources of energy that we have. Doing that is a huge dilemma of a social and political nature, but there are some technical aspects that I can speak about as well. First of all, what can we do about the greenhouse effect? One suggestion is a giant parasol at L1. L1 is the Lagrange point, about 1/100th of the distance from the center of the Earth to the center of the Sun, where a body could stay in orbit with a period of 1 Earth year. We recently sent the Genesis spacecraft to L1 and stayed there for 3 years and came back, so we know how to do it. The giant parasol could be a parasol 2,000 kilometers across, 1,200 miles across. It would reduce the solar flux at the Earth by 2%, and we could go on burning fossil fuels to our heart's content. It is probably feasible, possible to do, but it's a very foolish idea. We've already seen that the solar flux at the Earth does not govern the fate of the Earth. The Earth could be a Venusian inferno or a frozen ice ball with the same solar flux. And the last thing in the world that a future energy-starved world will need is a permanent spot on the face of the Sun. Another suggestion is to sequester the carbon dioxide so it doesn't go into the atmosphere. That's a very good idea. The question of how to sequester it has not been solved. But even if you could sequester it, the question is where to put it. It can be put into gas and oil wells, where it helps pump out the gas and oil, and that's being done successfully by some oil companies. But the capacity for carbon dioxide in those repositories is very small. Much more is needed, and that's an unsolved problem. Solar energy is, of course, a vital source of energy. One source of energy that's basically solar is hydroelectric power. The enormous pressure at the bottom of a reservoir turns a turbine and creates electricity. The water runs out of the bottom of the turbine and evaporates and rains back into the watershed, where it gathers again in the reservoir. So that's an apparently renewable source of energy. 100 years ago, that seemed like a wonderful idea, and dams were built just about everywhere they could be. Today, dams are probably being disassembled faster than they're being assembled because we've learned some of the disadvantages of dams. But in any case, you can't expand the hydroelectric power to substitute for the missing oil because it's already saturated. We've built dams wherever they can be built. Wind is becoming increasingly popular, especially now with increases in the efficiency of wind turbines and government subsidies for their use of renewables. It's almost comparable to coal as an economical source of energy. But the wind doesn't blow strongly enough and steadily enough in most places to be a realistic substitute for any of the sources of energy that we have. We may inherit the wind, but we will never learn to live on it. It will always contribute, but only a small amount. Biomass means you grow something and burn it. That's the way the world lived until 200 years ago. The principal problem with biomass is that it's extremely inefficient. Only about 1 2/10% of the sunlight falling on a given land area gets converted into chemical potential energy by biomass. So biomass will always be a contributor, but it will never be a significant one. The gold standard today for the use of solar energy is photovoltaics, PVs. In order to make 10 terawatts, that's the amount of energy we use from fossil fuels today. In order to make 10 terawatts of energy from photovoltaics, you'd have to cover some 220,000 square kilometers with photovoltaics. That's not a huge land area. It's about half the size of the state of California. There's lots of unused land in the world. You could conceivably use that much land, but all of the photovoltaics made up to the present time would probably cover about 10 square kilometers. To make 220,000 square kilometers of photovoltaics is an enormous challenge, probably beyond our ability to do it. On the other hand, the total solar flux, the total amount of solar energy that reaches the Earth is about 20,000 times that 10 terawatts. And so we are awash in solar energy. We just have to learn how to use it. We haven't begun yet to learn how to use it. Conservation, obviously, is a way of ameliorating the problem. Amory Lovins of the Rocky Mountain Institute recently wrote an article about conservation. He says that ultralight strong materials can be used to make cars that are more efficient than our present cars. We could all drive hybrids. I drive a hybrid. There's no reason why you can't. We can make our buildings and factories more efficient. We can make fuel from switchgrass and poplar, and I've added sugarcane to his list because sugarcane is the one fuel that's actually used. Brazil distills ethanol from sugarcane to substitute for about half of its gasoline. But Brazil has a warm climate and can grow sugarcane. We in the United States can't. Efficient electricity can be used more efficiently. You can have feebates, which gas-guzzling cars pay fees that are rebated to efficient cars. That's the kind of social engineering that our politicians are loath to do, and so on. Nuclear energy is obviously an important source of energy. Geothermal energy is a form of nuclear energy because geothermal energy comes from the heated interior of the Earth, heated by the decay of radioactive materials, uranium and thorium. It's used in various places for space heating, but using it for power is much more difficult because there are only a few places on Earth where a geothermal source reaches close enough to the surface of the Earth to be used for creating power. And when it's used for creating power, it's often found that it's exhausted faster than the Earth can replenish it. So geothermal energy will always be a source of energy, but never a dominant source. Fission is the kind of nuclear energy that we know how to use. We have not built a new fission plant in the United States for many years. And in most parts of the world, it's fallen into disrepute because of the fear of people of nuclear energy. Nevertheless, it is the most reliable source of energy that we have. On the other hand, to make the 10 terawatts of energy that we now use in fossil fuels would require 10,000 gigawatt plants. A gigawatt is about the biggest plant you can make. it would require 10,000 of those to make the 10 terawatts, and 10,000 of the largest nuclear plants imaginable is an almost unimaginable feat. So once again, there's a difficulty. Also, the reserves of uranium, known reserves of uranium, would only last for 10 or 20 years at this rate of use, and so that is a bridging technology at best, not a permanent solution. Fusion is a possible solution. Fusion is the one technology in which a great deal of money has been invested, and it has not been solved yet. It has been said of nuclear fusion and shale oil that they are both the energy sources of the future and always will be. But if we solve the fusion problem, if we manage to build a plant that gave us more energy than it took to create the fusion, it might solve our problems forever, because the deuterium in 1 gallon of seawater has the energy content of 300 gallons of gasoline, and it would probably last forever. Transportation is still a problem. Even if we solve the other problems with fusion energy, there's not going to be fusion cars or trains anytime soon. However, advanced batteries can be charged with these stationary power plants, or hydrogen can be created. Hydrogen can be used in internal combustion engines or in hydrogen fuel cells, or it can be used to combine with carbon dioxide to make other fuels. So we understand the basic principles that would make it possible for us to have a civilization as complex as ours without using fossil fuels, but we have not embarked on that at all. This is a picture of the United States at the moment of the Great Blackout, 23:15 Eastern Standard Time and 14th of August 2003. And you can see that a big bite has been taken out of the Northeast. That's because a power line, a tree fell on a power line somewhere in Ohio, and the whole Northeast went out. This picture was probably faked, but it serves to remind us of the situation anyway. With that kind of vulnerability, you can see that we are very vulnerable indeed. Scientists are supposed to make predictions. When a scientist analyzes a situation, he's supposed to predict some new result from that analysis. The prediction, you hope that the prediction will be correct because it shows how clever you are, and you know that making the prediction will not affect whether it's correct or not. I'm going to make a prediction of a different sort. I predict that civilization as we know it will come to an end sometime in this century when the fuel runs out. I hope that I'm wrong, and I hope that simply making the prediction will help to make me wrong, because some of you will pitch in and get to work on this problem and solve it. Every university that I know of has some effort along the lines that I've been discussing. The largest that I know of is at Stanford University with the Global Climate and Energy Project. It's run by my friend Lenore. Toyota, ExxonMobil, General Electric, and Schlumberger have put $225 million into this project over a period of 10 years. That sounds like a lot of money, but it's actually only a drop in the bucket. But this is one project. At Caltech, we have a smaller, more focused project called Powering the Planet, Caltech's Center for Sustainable Energy Research, where applied physicists, chemists, and material scientists work together on harnessing solar energy principally. And Stephen Koonin, who was the provost of Caltech, left Caltech about a year ago to become the chief scientist at British Petroleum at BP, one of the most important energy jobs in the world. So you can see that we at Caltech have made our contribution to this problem. I asked myself what contribution I could make. I don't know anything useful like these people do. I'm just a physicist. And so I thought about it, and I decided that what I could do is to write a book about it, and I've done that, and I thank you very much.
much, Dr. Goodstein. We will have a few questions now. Please use the microphone because this is being webcast. See where the microphones are. If you'd identify yourself, your organization, that would be helpful, if you don't mind.
Arthur Collins, Planning and Technical Support Division, ARB. You mentioned, if I understood you correctly, that the uranium supply would be like 5 to 10 years. My question is this strictly the U-235? So it doesn't include breeding of U-238, and it doesn't include the thorium reserves?
Yes, that's correct. That's correct.
My understanding is with those total reserves, you're talking like 500 to 600 years rather than 5 to 10.
Yes, if you could use breeder reactors and breed plutonium from the uranium, you would increase the amount available by a factor of 100. And so the challenge is to make the world safe for breeder reactors, but that's a very tall order. Thorium is another possible use. There's 3 times as much thorium in the Earth's crust as there is uranium. So far, thorium has not been much used in reactors, but it could be, and so it could become a resource.
Earl Withicum, PTSD, Air Resources Board. Can you comment on our ability to feed the world's population when the ammonia that we convert to fertilizer that derives from natural gas is gone?
Yes, I mentioned that in passing. We derive ammonia from natural gas, and when that's gone, the world's population will probably have to return to its pre-industrial level, which is a few 100 million instead of 6 billion. I don't see any solution to that problem unless we can find another source of the ammonia. That's the green revolution that I discussed before.
Jerry Wiens, California Energy Commission. If we assume that global warming will eventually cause the methane hydrates to be released into the atmosphere and accelerate global warming, wouldn't it be a better idea to try to produce it?
To produce what?
The methane hydrates?
Well, methane hydrate, nobody knows how to use it yet, and it may be that using it will release it into the atmosphere and greatly increase the greenhouse gases. So that's a big problem. I don't know that producing methane hydrate would be any better than using the natural methane hydrate.
Hi, Tom Shefflin, library patron user. Would you be willing to autograph some books for the Sacramento County Library at the conclusion?
Yes, yes, I'll be happy to.
Yeah, I'm over here. Yeah, I'm Bill Dean with Air Resources Board. You mentioned when they ran out of whales, they shifted to oil, and when they ran out of trees, they shifted to coal. Were those transitions fairly painless, or were they fairly wrenching?
I think that they were fairly painless because the usage was very small at the time. Now we're thoroughly dependent on oil, and the change will be painful.
Chuck White with Waste Management. About 20 years ago, it seems to me there was a theory, and I can't remember the exact name, but I think it was called Gold's theorem, that there was this possibility that oil was really not so much from fossil fuel, but from leftover organic molecules from the formation of the Earth at the center, and it was all bubbling to the surface. But I haven't heard much about that recently. I think I know the reason why, but I would ask you to comment on that, please.
Well, it's been largely disproven, and very few people believe in it. There was a big dig in a place where there was not supposed to be any oil to see if Gold's theory was correct. They found about 80 barrels of oil, but they thought that came from the digging process itself. And the net result is that it's been largely discredited, and very few geologists believe it.
I'm sorry. My name is Muriel Strand, and I retired from ARB about a year ago. In the discussions that I hear, sort of part of the general social discussion that's starting to happen about this, very few people ever talk about the amount of energy that's required to actually make capital goods like photovoltaic panels, like cars, like all of this sort of thing. I'd just be interested in your thoughts about that general arena.
Well, we need to replace an immense amount of energy, all of the energy that we use, whether it's to make cars or to heat our homes or for whatever other reason. We need to replace all of that energy, and that's going to be very difficult to do. I don't know how much energy is used to make cars and so on, but the amount is huge.
Professor, you're leaving us in a state of despair here. My name is Ivor John Ryerson, Master and Associates. I think you've portrayed the facts, but at the end here, we don't see any solution. I think that what we must have is a vision of solving this problem, and I'd like you to comment on that before we leave the room, please. Thank you.
I think that if our political leaders challenged the technological community to replace fossil fuels, to kick the fossil fuel habits in 10 years, let's say, and gave us the resources to do it with, we could do it. But we lack the kind of visionary leadership that would be required to do that at the moment. On the other hand, 2 years ago when I wrote this book, I was a voice in the wilderness. Nobody was listening. Nobody was paying any attention. Now it's become mainstream. You see references to this everywhere. The President mentioned it in his State of the Union address. So it's dawning on people that this problem exists. It's happening very quickly, and I have hopes that we will kick the fossil fuel habit and learn how to use alternative sources of energy.
I have a question from one of our webcast viewers, Deborah Neidert. Assuming you saw the Al Gore movie, Inconvenient Truth, do you have any major issues with the movie? That is, was it accurate in your mind?
Yes, I thought it was very accurate, and I thought it was an excellent movie, and I recommend all of you to go and see it.
Hi, Ed Bonelli from Department of Toxic Substance Control. I was wondering if you could speak on the efficiency of photovoltaics as it stands now and whether it's a viable technology and how soon it would be a viable technology.
Okay, the photovoltaics, typical photovoltaics now are about 10% efficient. That is, about 10% of the sunlight falling on them get turned into electrical energy. You can make much more efficient photovoltaics. You may have noticed the traffic lights around the city have become sort of speckled and much brighter than they used to be. Those are LED arrays. 10 years ago when I was working in this field, people used to talk about why LEDs were so inefficient. But over the years, clever engineers have figured out how to get the light out of the LEDs, and now they've become extremely efficient. And you can put your hand on top of a traffic light and feel that there's no heat whatsoever. And so LEDs are a new technology that's transformed a certain fraction of our lives, that is traffic lights. A photovoltaic is just an LED running backwards, because an LED takes electricity and turns it into light. A photovoltaic turns light into electricity. It's the same kind of semiconductor running backwards. So you might think that you could make very efficient photovoltaics, but you can't, because LEDs work at one color only. And photovoltaic, in order to be efficient, would have to convert all the sunlight falling on in all colors into electricity. You can make efficient photovoltaics by layering them various different semiconductors together, but they're extremely expensive, and they're used only in spaceflight applications today. They may become better in the future. but 10% is the standard efficiency today. They may go up to 30% or 40%, so a factor of 3 or 4 gain, but that's all. So I have high hopes for the future of photovoltaics, but there are limitations.
Thank you. I'm Paula Lamazzi, and I didn't want people to be too discouraged or thinking that since we're not replacing the fossil fuels with other technologies that we're all lost, because there might be other solutions. There's like a growing movement of community members around the country, around the world, like the Post-Carbon Institute, and where communities are planning to change the way we live, because we're living incorrectly. We should be like growing our own food. One of the alternatives to petroleum-produced ammonia is urine. And just like that's just one example. But there's a way to live correctly that is not consuming so much energy of any kind.
Yes, there are vast improvements that we could make on our consumption of energy, and I hope that we will be making them. And I hope that you're right.
Bob Horowitz, Waste Management Board. I think the vice president was sort of famously quoted as saying, energy conservation was a personal virtue, but that it was sort of unimportant. And maybe this takes off a little where you were leaving off. But is there some way that conservation or whatever fuel conservation, as you said, on a massive scale, could stave off some of what you're talking about here?
Yes, fuel conservation could stave it off, but not prevent it permanently, because we will run out of oil eventually, no matter what. But fuel conservation is an important first step, yes.
Simeon Okorike from the Air Resources Board. It seems like every aspect of our life is touched one way or the other by petroleum products. Are there any major studies to find replacement for things like because things like products we found in building materials, seeds, road paving, and other products that are part of petroleum products?
I'm afraid I didn't understand the question. Could you repeat it?
Okay, I said that almost every aspect of our lives are affected by petroleum products, derivatives from petroleum. The seat we're using right now, the clothes we're wearing, the shoes we're using, almost everything has some aspect of petroleum product in it. My question is, do we have any studies that are geared towards finding replacement for those materials?
I'm sorry, I didn't hear the question. Repeat the question again.
Maybe I can help.
Yeah.
He was pointing out that many of the things that we use, clothing, roads, are derived from petroleum.
Yes.
And the question is, are there reasonable substitutes for the petroleum source as a raw material?
That's a very good question, and I don't know the answer to that. Because we have petroleum and we use it, there presumably are other things that could be used. I don't know. I don't really know what the answer is.
Tony Van Kuren, Air Resources Board. As a physicist, can you give us your guess on the odds of success of the ITER experiment?
The ITER experiment is an international collaboration to build a thermonuclear reactor, that is to say, a fusion reactor. And it recently chose a place for the ITER reactor to be built. I think that probably it will succeed eventually in break even. Up to now, people have succeeded in getting back about half the energy that they put into thermonuclear reactions. The ITER would be designed to become energy positive so that it would give back more energy than it took to create the energy in the first place. I believe that it will be successful eventually, but that's very far from a useful nuclear reactor. So that's my answer.
Previous speaker spoke about substitutes, and the question of fusion power just came up. I'll make the comment that if you have enough energy in a visionary long-range future, let's say fusion, you can do just about anything. For example, you can extract carbon dioxide from the air and take hydrogen from water and make hydrocarbons. So given enough energy, cheap enough, you can do just about anything you want.
That's quite true. That's quite true, but we don't have enough energy.
That is true. That's why I said visionary.
Alberto Ayala with the Resources Board. The first point you made was the fact that fuel is too cheap. Would you suggest that then taxation on fuels is a step in the right direction?
Yes, I think taxation of fuels would be a step in the right direction. I don't think our politicians are prepared to do that yet, but it would certainly be a step in the right direction.
Chuck White with Waste Management again. Going back to your somewhat sobering prediction slide, there was an article in Science some time ago that suggested that we have a window of opportunity while we still have extra fuel and extra energy to be able to make the transition to fusion power or to photovoltaic. But if we miss this window of opportunity, then there won't be any excess energy, and there'll be such a competition for the energy resources that we won't be able to marshal it to be able to make that leap to the next level, energy level. And I was wondering if you could comment on that outlook.
I agree completely.
Quick question. Do you have any comments on nuclear waste?
Well, nuclear waste is a technical problem, and we're very good at solving technical problems. And so we will eventually solve the problem of nuclear waste. The solution that we have now are not so bad. The nuclear waste stays at the place where it was created and goes into pits and so on. The solution of creating a depository where it would last for 10,000 years without causing any difficulty is blue sky and ridiculous, because 10,000 years is just an arbitrary number. But I believe that nuclear waste is a big problem, but we should be able to solve that problem.
Dr. Goodstein, we have a question from Andrew Yoon from our Mobile Source Control Division. Cambridge Energy Research Associates came out with a report just last week saying that a world oil reserve is at 4.8 trillion barrels, and concluded that the world's oil production will not peak until 2032. This is in a sharp contrast with commonly quoted 1.2 to 1.8 trillion barrels. Would you care to comment on that?
Well, the extrapolation method that I showed you that Hubbert created can be applied to the world supply, and it gives a pretty good extrapolation to 2 trillion barrels. I don't know where they got the number of 4.8. Their idea that the peak will come in 2030 is consistent with my idea that it might be 20 years off. And so I don't see very much difference between their view and mine.
I just wanted, Muriel Strand again, I just wanted to speak to the gentleman who was asking for a hopeful outlook. I would advocate a system of small villages surrounded by farms. We need to start growing our own food. We need to revive traditional crafts. Books like Starhawk's The Fifth Sacred Thing and Ecotopia somewhat describe these sort of in the background of their stories.
Yes, that's true, but you're describing a different civilization from the one we have now.
Technology and civilization are not the same thing.
Well, you are describing a different civilization.
That's
from
true. But it's civilization, and we can do that.
I think that's enough.
How about one or two more? Okay, well, we'll take one more web question and then one more from the audience. So the question was, do you have or do you know of any theories of why petroleum reserves are concentrated in what is generally known as the Mideast?
Just an accident of nature. That's where the oil was made, and that's where it's found. But I don't know how much the reserves are in the Middle East. I doubt that it's as much as they claim because of the discontinuous increase that took place in the late 1980s. But you never know.
Okay, one last question here, or with the mic.
Yes, Mike Leon with the Waste Management Board. I was curious, in your talk, you mentioned that as costs increase, we're going to see economic effects. And I was wondering when you would anticipate, or if there's any studies out there that indicate when we can expect to see these economic impacts on our global economy and where large economic systems are really affected.
I didn't understand the question. Could you repeat it, please?
Okay. My question is, our global economy dependent on cheap fossil fuel. When do you anticipate to see really significant economic impacts due to the increased costs of fuel?
Well, I don't know. I don't know exactly what's going to happen. I can't predict the future. The volatility of oil prices in recent times implies that we're close to the maximum, and so it might be right now that it's happening, or it might not happen for another 10 or 20 years. I just don't know.
Okay, well, let's thank Dr. Goodstein for Thank you. Very good.